Let's try this mic one more time. Not ready. I have to set up the streaming for Taida again. No, because the students at NTU didn't complete their exam, the mid-semester exam. They're supposed to. So I decided that I would stop streaming to them. I have to set up the streaming for Taida. And it seems like after I made that threat, then they got around to it. No, because the students at NTU didn't complete their exam, the mid-semester exam. Are you guys enjoying my computer? So I decided that I would stop streaming. Is it working? Sorry? It goes like a jet airplane taking off, I know. Yeah, but you installed, it's a good computer. CentOS? Is it working? Did you install the Intel compiler? Sorry? That is the next step. 我还没有跟你们说明，但是里面的 Intel Xeon Phi 你一定要先安装那个 Intel compiler，以后就有办法用它。CentOS? Did you install the That's the second thing you install. Yeah, CentOS first, then NVIDIA. Yeah. Use what? The NVIDIA what? That's the second thing you install. Yeah. Never heard of it. Does it work? 所以现在可以跑酷的计算吗？你现在可以用那台跑酷的计算吗？ Okay. Are we ready? Have a seat, guys. Jose, have a seat. Right, GPU is finished. No more GPU. Doesn't that make you feel good? Okay. Not really, because you probably have to do GPU anyway later on in your own research. But from this point on, we're not doing GPU anymore. We're over to the multi-core CPU part. You'll be happy to know that if you can do GPU, then this multi-core CPU stuff is very, very easy. Because the hardest part of parallel computing has all been taken care of in the GPU part. So fortunately for us, we can move on to the easy stuff now, real computing. And it's important that we talk about this because the computer that you guys are running on, the computer that you guys connect to every day in class is my personal computer. That's not the school's computer. And that computer has 32 CPU cores inside. When you guys run on the Tesla that is inside, there's a Tesla GPU that you guys are using to do your calculations in that machine. Actually, the CPUs inside that machine are faster than the GPU. So if you really wanted to run a high-speed calculation using that machine, you wouldn't do GPU because the CPUs inside that box, when I got it, were the best CPUs on the planet, and there are a lot of them, and there's a crap load of memory too. So, I've taught you GPU computation. That takes advantage of the GPU devices, but I've never shown you how to take advantage of multi-core CPU, and I think it's about time. So until now, we've done parallel computing on the GPU. It is a very good idea because, to be honest, the best GPU in the world will set you back. Well, right now the Titan 5 is $3,000 US. That is a good GPU. You can't even buy it in Taiwan. It pisses me off. But that's okay. You guys can still buy the 1080 Ti for about 25,000 块. The 1080 Ti is a good device, and it costs 25,000 NT. The machine that you guys are using for this computation, this course, comes in at around 41. It is much more valuable and much more expensive than just a GPU device. So using GPU is good because you, for a very small amount of capital, can do parallel performance in quite a large period of time. Sorry, in an efficient amount of time. But let me tell you, when you get a job or when you go to a conference, not many people use GPU yet. There are a few, quite a few, and it's a growing number. But by far and large, when we talk about parallel computing, we're not talking about GPU, we're talking about using multiple CPU cores. 所以，我不知道你们知道超级电脑是什么吗？ Yes, that's what I'm talking about. That Taipei City Council meeting. when we talk about parallel computing, the conventional definition for supercomputing is the use of multiple computing nodes working together to solve a supercomputing problem. So, when you hear the words supercomputer, it is actually a bit of a misnomer. There is no such thing as a supercomputer. All there is a lot of normal computers or above average computers connected together, working together to solve a problem. So when we look at multi-core CPU, actually, we have to think about both of these definitions. The one that you might be familiar with is here, but I want to talk about this one first. Conventional supercomputing is where we connect a large number of single motherboards with some kind of network interface to a switch. If you have no money, you'll probably buy a few standard computers and use some LAN cables to connect to a normal switch and create a cluster this way. If you have a lot of money, you'll buy some very fancy nodes, but you'll still connect them to a switch, but you won't use a LAN switch. You'll be using an InfiniBand switch, and InfiniBand connectors and InfiniBand devices inside each of these. These are just devices which enable high-speed networking. At the moment, in a supercomputing cluster, these lines here that you see here might look like LAN cables to you. We might replace these with InfiniBand cables which provide communication speeds of about 40 or 50 gigabits per second. Right now, if you're using a LAN cable, the fastest you'll get is 1 Gbps, 1 gigabit per second, 1000 Mbps, 1000 megabytes per second. Doesn't matter. The whole point is, when some people think of supercomputers, they're probably thinking of a single super big supercomputer. These things do not exist. Only 5 countries have such devices, and they're crap. What we actually do is buy a whole lot of normal computers, store them together, network them together, and then we use a method called an API called MPI to allow communication between the nodes. This is what a supercomputer is, essentially. The details of the interconnect change between machines, the details of each node change between the machines, but they all follow this concept. By using this, each node has its own motherboard, own hard drive, own memory. If we want to allow this CPU to communicate with this CPU between 2 different nodes, we need to be able to exchange information across this network using TCP/IP communications normally. This way is quite complicated to set up. Some of my students will know. It is quite expensive because for every node we have to buy power supply units, hard drives, things that you only need to buy one of if you only have a single motherboard. And we also need to buy these switches. A gigabit switch might only be a few thousand NT, but an InfiniBand switch might be 1. So these are expensive devices. So clusters like these, supercomputers, are expensive to produce. The other kind of parallel computing that we might use for CPU is this one here. Now what you're looking at is a die of a modern CPU. Nowadays, when you go to buy a CPU on coolpc.com.tw or PC Home, where do you guys go to buy stuff now? Don't go to 3C. Just don't go there. Go anywhere else. When you try to buy a CPU, to my knowledge, you cannot buy a single core CPU anymore. Every CPU that you can buy contains multiple cores inside. It has a single socket, so each chip that you buy is a single socket chip. It goes into one socket on the motherboard. But inside that CPU socket, there are several cores. They are distinct cores. They share some cache. By looking at this, you just know it's the first generation Sandy Bridge. Modern CPUs now contain integrated graphics. When most of you buy laptops, if you're not careful, you'll buy an integrated graphics laptop where the GPU that drives the laptop is actually inside the CPU core itself. You don't want to buy that kind of laptop. So if you're going to buy a laptop, come talk to me first. But most cores now, this is an Intel core obviously, from this. Most cores look like this. By doing this, we have multiple cores which operate in the same chip. All of those cores have access to the same memory, the same storage, the same motherboard. So to allow cooperation between these 2 cores, we do not have to worry about the network communications that we use here. Because each of these cores has access to the same memory. So if you want cores to communicate, they can copy data to memory and then use the memory to allow communication between the 2 cores. So, the definition of the type of parallel computing that we use for these two mechanisms all comes down to how the memory is distributed. In the left case, in this case, we have many CPUs in many separate nodes. Each CPU has its own motherboard. Each motherboard has its own memory. So all of the memory in the cluster is distributed across each of the individual nodes. In this system here, we have a single motherboard with a single or multiple sockets. But the important fact is each of the cores has access to the same memory. So the same memory on the motherboard is shared across all of these cores. So on the right-hand side, if we're going to do parallel computing on the right-hand side, we call this shared memory parallelization. Shared memory. GPU is a kind of shared memory parallelization because all of the cores on the GPU have access to the same global memory. So shared memory. On the left here, the memory is distributed. We call this distributed memory parallel computing. So shared memory parallel computation is the focus of this course. We've done shared memory until now on the GPU device. And we're going to continue using shared memory parallelization for the next part, which is OpenMP. In reality though, because you can't buy a CPU that doesn't have multiple cores, when you build a distributed memory supercomputing cluster, each one of these nodes is going to have a CPU with multiple cores inside, which means that every real-life supercomputing cluster uses a hybrid, a combination of shared memory and distributed memory parallelization. So if you can write, supercomputing cluster, they act as one CPU. Yep. So in the very fancy workstation that your lab just acquired, it's like it's just got one fat CPU, even though there are two physical CPUs. So here we are. This, any supercomputer, any Talji DNR, is a combination of local shared memory parallelization and distributed parallelization. So in reality, if you want to write a code that runs efficiently on a real supercomputer, you need to use MPI to allow the communication between nodes across the TCP/IP LAN connections. Then you need to use OpenMP on each node to share the work across all of the cores on that node. There's still a lot of students writing papers about this kind of hybrid parallelization at the modern conferences right now. So if you guys wrote a code that uses MPI and OpenMP, you could publish it next week. It's still a hot area, because not a lot of people know what a supercomputer is. I'll show you guys the YouTube video later. Did you see the YouTube video that I'm talking about? Oh, it's in the news. My wife showed it to me. So, why is shared memory so important now? Let me tell you a secret. 20 years ago, there was no shared memory parallelization. Every CPU core that you bought before P4 had a single CPU core. There was no such thing as shared memory because every motherboard had one physical core in each chip. So shared memory didn't exist. It is funny though that OpenMP that we're talking about today did exist then, but regardless. Back in those days, 20, 30 years ago, if you want to do parallel computing, you only have the left-hand option, the distributed memory cluster. That was what we were doing 20 years ago. But nowadays, shared memory is increasingly important because we have GPU cards, and we have cores like this. Now, you can't see that very well because the projector is projecting the incorrect colors twice. On this die, there are actually 18 cores and 2 controllers. So this is a single Intel chip. It is the i9-7980 core. One of these chips costs Liuan Kuai. I can't afford to buy one, so if you guys buy one, please show me. I'd like to see what it looks like. There are 18 cores inside this chip. Just 18 inside the single chip. So this is a single Intel chip. You have 2 ways you can parallelize your codes on this chip. You can use MPI as a matter of fact, but MPI is designed for networks. There's no point in using MPI for this. You're better off using a shared memory parallelization method to share the computation work across these cores because each of these cores sees the same memory. So we can use shared memory no problem on these cores. And because 如果你看我们最近10年我们的 CPU 这么改变了，如果你看2003 or 2004, the first Intel Core 2 Duo CPU came out. That had 2 cores. 如果你真的有兴趣看一个 Core 2 Duo, go to the mechanical engineering building to the 6楼, you'll still find some of those computers in there. It's like a museum. After that came the 4-core series. So actually, the Q-core series and the P-core series from Intel, they all had 2 and 4 cores. Then the Sandy Bridge Intels came out, they had 4 cores. Then Ivory Bridge came out, they were still stuck at 4 cores. But then we started to see some Xeon cores come out with 8 cores. This is a Skylake X chip. Skylake X just has 18 cores. If you look at AMD, AMD have just gone crazy because AMD invented multi-core. AMD had 4-core chips way back when, before Intel had them. And now you can go buy an AMD core that has 64 cores inside a single chip, if you want to buy an Opteron server. So by buying these devices, you can see the number of cores inside each CPU is increasing at a high rate. So the number of CPUs available for us to use in each CPU socket are increasing. The biggest problem is, how much power does this chip use? It can't be any higher than 100 watts. That's about right. If you go higher than 125 watts, things start to melt on this. So the problem is, if you have 18 cores, but the total power is fixed, that means the frequency for each core is lower to compensate for that. Or they use more efficient transistor design, which is what they were doing recently, the 3-layer transistors, the 3D transistors. So if we want to take advantage of this computational power, if we want to use all of the transistors on the chip, we need to use these cores as part of our computational program. We can't use CUDA to program these, so we need to use something else. Now, why do people enjoy shared memory computation? You can buy 1 or 2 sockets, buy 1 or 2 chips, put into a 1 or 2 socket motherboard. You don't have to buy 2 motherboards, you don't have to buy twice the RAM, you don't have to buy 2 hard drives, you don't need 2 cases. You just buy 1 case, 1 PSU, 1 set of RAM, 1 hard drive, maybe 2 hard drives. And then you can put as many cores on there as you like. You can get motherboards now that have 8 sockets on them. If you really want to go crazy, you can go to Supermicro, get a big, gigantic motherboard, it's like this fat, and you just plonk 8 Intel Xeon core sockets on it. Actually, the 8 one is AMD. You can plonk 8 AMDs. That means you've got 1 motherboard that has 8 times 64. That's a damn lot of cores. I'm not going to do the math. You guys can do the math on your own. Like 500 cores. That's a big number. But you only have to buy the memory, hard drive, power supply once. So University of Queensland and most of the universities in Australia have stopped doing this kind of parallel computing. They've just given up. Most courses now, when we do parallel computing, use shared memory because we can create a shared memory computer that has powerful parallel computational capacity for a relatively small price. We don't need to switch. We don't need to worry about high-speed connections. We don't need to worry about installing MPI or any of the virtual file systems. So, good news for you guys. You've already done GPU computing. GPU is shared memory computation. But GPU is hard because you need to send information to the device, get it back. If there's a problem on the device, the GPU can't tell you about it. The only way you will know is if you copy data back and check the data manually. 你们现在应该都习惯做这个工作. Everyone here has found their bugs in GPU code. Hey, is there anyone who has not found a bug on GPU? I hope that everyone here has found a bug on GPU. That's what you are here for. You are in this class to find bugs so that I can train you to know how to fix them. But programming using OpenMP is so easy because before, when there was a bug on GPU, GPU can't tell you. This time, the CPUs can tell you, and they will tell you a lot of information. So it's actually the exact opposite problem. The CPUs this time, if there's a bug, will tell you too much data. But they will tell you, and you can't be angry at them because they did tell you about it. So debugging an OpenMP code is much simpler than debugging a GPU code. So you guys should be pretty straightforward. We can use printf on each core, on each thread, and it will talk, which means that every thread will say hello if you write printf hello. We're going to use OpenMP for this. OpenMP is not the only way. It is probably the best way. OpenMP works on any operating system. We can use Linux, Windows, ARM. I've developed OpenMP applications for mobile phones, for MP3 players, for computers, everything. OpenMP is an API that can run on basically any machine and in any language. So if there is some crazy person in this room who is doing Fortran because some crazy CFD professor wants them to use Fortran for their assignment, if you want to do OpenMP parallel computing in Fortran, it is almost identical to the material I'm about to teach you now for parallel computing in C. OpenMP doesn't actually change between the different programming languages. It doesn't change much. So if you really want to do parallel computing in Fortran, a lot of people did, you can be my guest, Google OpenMP Fortran. You'll find a lot of information. There are some people who do Fortran programming in GPU. I didn't teach you guys that because you're not that crazy. So how does OpenMP work? It is different to GPU. In GPU, GPU is like taking your daughter to the toilet for the first time. You need to tell it to do everything. It doesn't know anything about it. So when you do parallel computing on GPU, all of the communications, all of the parallel computing work, how you share the work is all manually done. OpenMP, automatic. OpenMP is mostly automated. So you don't have to worry about a lot of things, which is why we do it. So when we use OpenMP, the way we perform parallel computing is through what we call compiler directives. To give you a summary of what it can do, OpenMP allows its threads to have access to all of the memory on the motherboard, which is shared memory. So all of the cores here, this here, I've got a lolly in my bag if anyone can tell me the name of that chip. To give you a summary of what it can do, it's an AMD X4640. It's a very good chip, Phenom 2. One of the best cores ever made. They're still really expensive because people like to mine Bitcoins and Ether, and they are good for that. So I'm not going to teach that in this course, although I could. OpenMP allows shared memory access, but the good news is OpenMP also allows each core to have access to its own private memory. Now this is very, very important because each core has its own work to do. If each core doesn't have its access to its own private piece of memory, then there's a risk that other cores, other threads might access that piece of shared memory and start to violate it. And then your computation is destroyed. So in reality, we need a combination between private and shared memory. OpenMP allows us to do this in a very easy way. And today we're going to do it. So by the end of today's class, everyone here should be able to write a CG code in OpenMP. It is that easy. It is a stupidly easy language to pick up. Something you need to know though, happens every year. Someone asks me, in OpenMP we create threads. These threads are just like GPU threads, but we don't create as many. So I'll tell you why. Well, the GPU is designed to accept thousands and thousands of threads. That's what it's designed to do. In OpenMP, we normally keep the number of threads about the same number as the number of cores. What happens if we create more threads than we have cores in OpenMP? They line up. 他们会排队。所以如果我们有5个 threads， 2个 CPU， 它可能是这样排。We can control how they line up, and we can control how many each core gets. We can control how often the CPU checks to see if there are any spare threads waiting. 那个是我们都可以控制，但是平常我们是用这个方式 Q. So, let's say you want to write an OpenMP code, but you only have a single core machine to write it on. You can still test it. You can still write the code and test it. It will just queue all of these threads across that single core. Another thing you need to know, I shouldn't need to tell you this. Every single application we develop starts with a single thread and ends with a single thread. In GPU computing, we have the main thread, which exists in main. Then we would create our GPU kernels, which would launch our functions in parallel. We would create threads then. They would do the work, and then we would get the result back. In OpenMP, it is very similar. We start with a single thread in main. Then we create many threads. They do their work. Then the threads are destroyed. We always finish a program with one thread. In OpenMP, you cannot compile your code if it does not finish with one thread. It won't let you compile it. It has a very smart system for detecting this.
Then we create many threads.
Now we need to be very careful here.
The threads are destroyed. We always
In OpenMP, I'm going to show you soon how to create threads.
in OpenMP you cannot compile
Now on the
your code.
GPU, until recently, you can't create threads after you create threads. So you can't launch a kernel and then from within that kernel launch new kernels. 最近的 CUDA 其实现在可以。我没有教你这么做的，因为如果你们这样对我的 GPU，you'll break my GPU.
Until recently,
So I didn't teach it to you, so you can't break my GPU. OpenMP is so easy to do. You can get each thread to create threads, which create threads, which create threads, which you get the idea? And then you break my computer. My computer, not the school's computer.
so I didn't teach it to you. So you can't
I know where you live.
OpenMP
We
is
can
so
create
easy
threads
to do.
within
You
threads
can
in
get
OpenMP
each thread to
easily.
create threads.
This is called recursive thread creation. Be careful. I wouldn't do it if I were you.
And then you break
All
my
threads
computer.
must be destroyed before the end of your program, so you must have a safe way of doing this.
I know where
Let's
you
do
live.
it.
We can create threads with
This is your first OpenMP code.
This is called recursive thread
This
creation. Be careful. I wouldn't do it if
doesn't look like much, but it has some very
all
important
threads
features.
must be destroyed before
One,
the end of your program, so you must
we
have a
don't
safe
even need this
way of doing this.
because we don't do anything with it.
Let's do it.
Here is the start of our program. Here is the end of our program.
This is your first.
This is our single thread that we start and end the program on. This has one thread,
Doesn't
no
look
more.
like much.
We start the program with one thread
it
and
has
we
some
finish it
very
with one
important
thread. So if we draw a flow chart of this
We don't
program,
even
it looks
need
like
this.
this.
Because we don't
Sweet.
do anything with it. Here is the start of our program. Here is
If
the
we
end of
want
our
to
program.
modify this
This
to
is
really
our
use
single
multiple
thread
cores,
that we start
there are
and
several
end
things we need to
program
do. In OpenMP, OpenMP is an API, so there are functions that we can use. In CUDA, because we're using the NVCC compiler, we don't need to include CUDA.h at the top of our code. You can if you want to, but we didn't, because we're using NVCC to compile our GPU codes. So the compiler, because it is a CUDA compiler, guessed that you're using NVCC because this is a GPU code, and 它自己帮你放进去.
Because we're using
Here,
NVCC compiler,
any CPU can compile any OpenMP code, so we need to include a header. The OpenMP header on every system, regardless of Windows, Linux, Fedora, whatever, is omp.h. So we need to include that at the top. Now inside omp.h, it is a header file which contains, prototype function declarations.
on every system,
These functions are very, very important for us.
Fedora.
There are several kinds of functions, but most of these are runtime functions.
So we need to include that at the top.
Let's do it.
Now inside omp.h, it is a header file.
Compiler directives is how we control parallel computing on thread creation in OpenMP. Now, we've used compiler directives before. You've seen me do
There
it.
are several kinds of functions, but most of these are runtime functions. So we need to include that.
Let's do it.
Now inside omp.h, it is a header
Compiler directives is how we control parallel computing.
file.
That is a compiler directive.
in OpenMP.
How do you know it
Now,
is a
we've
compiler
used
directive?
Compiler directives before.
That
You've
hash.
seen me do it.
That hash is a special symbol which tells your compiler, hey compiler, this is something special that you need to pay attention to. Define, then by using define, we replace the symbol n wherever we find it in the code with a number
How do you know
100,
it is a compiler
which is
directive?
why you can't do that.
That
If
hash
you
is
write
a
that,
special symbol which
it
tells the
replaces
compiler,
n
"Hey,
with
compiler,
equals
this is
100
something
dot dash.
special that you need to pay attention
You're
to."
going to cause a segment.
Define,
Your code won't
then
compile because it's
by
incomplete
using
code.
define, we
which
replace
is
the
why
symbol n wherever we
you
find
write
it in the
that.
code with a number 100.
I'm sure
is
everyone here has
why
had
you
this
can't
bug at least
do
once.
That.
I'm glad that you had an opportunity to
If
discover
you write
this.
that, it replaces
That is
n
one compiler
with
directive.
equals 100 dot dash. You're going to cause a segment. Your code
In this
won't
case,
compile because it's
our
incomplete.
compiler directives all start with pragma.
You write that.
Hash pragma.
I'm sure everyone here has had this bug.
That is what we're doing today.
I'm glad
When we want to pass on something to OpenMP, we
that
pass
is
some
one
pragmas.
compiler directive.
Oh yeah. Examples.
In this case,
We're
our
going to
compiler
use
directives
hash
all start
pragma
with
to pass instructions to the compiler. These compilers are going to pass instructions onto the compiler regarding how many threads we create,
We pass them pragmas.
what variables we use, if these variables are private or shared, how we parallelize the work,
We're going
and
to
what we
use hash
parallelize.
pragma.
所以其实我们所有的 code，所有的最重要的 instructions 都是 pragma。 hash pragma.
the compiler regarding
And this is how OpenMP works.
what variables
Let's do it.
we use,
I'm
if these
itching to get some
variables are
code
private
going.
or shared, how we
Oh,
parallelize the work,
yes,
and what
here we are.
parallelize.
The
So
other
we
pages
choose
were just useless
soil
information that
code,
you should read up
soil
on
the
before the end of the course.
instructions.
如果你们要在家里要自己做 OpenMP 的话
And this is how OpenMP works.
you might want to read some of these.
Let's do it.
Environment variables
Itching to get some code going.
are constants inside your operating system which pass information onto OpenMP to your
The other
compilers
pages were just useless
so that they know what your default system settings are.
information.
In Windows, they are stored in your registry, which means you can't touch them
To read some of these,
unless you're going to edit the registry, which is dangerous. But everyone knows how to do it. It's regedit.exe. You can go anywhere. In Linux, it's somewhere else, and you can set them from the command prompt. I want me or Johnny because I don't want you to touch my important system parameters.
which means you can't
But
touch
if you have your own computer system, you're going to need to.
edit the registry, which is dangerous.
This is your first OpenMP code.
Do it. It's regedit.exe. You can go
Can everyone please code that up, please?
in Linux.
Right
it's
now.
somewhere else.
Log into the terminal, write this code. This code is correct. There are no bugs. If your code does not compile,
But if you have your own,
you copied it wrong.
going to need to.
It's there and there. If you can't read it, come and take a photo. I'm sorry I haven't put these notes on the internet yet.
Please code that up, please. Right now. Log into the terminal. Write this code. This code is correct. There are no bugs. If your code does not compile, but if you have your own, you copied it wrong. It's there and there. If you can't read it, come and take a photo. I'm sorry I haven't put these notes on the internet yet. Right now. Log into the terminal. Write this code. This code is correct. There are no bugs. If your code does not compile, you copied it wrong. It's there and there. If you can't read it, come and take a photo. I'm sorry I haven't put these notes on the internet yet.
All right, but first let's talk about what we see here. We've got our start. We include our things up here, stdio.h for printf. OMP is for our pragmas and, well, not necessarily our pragmas, but any OpenMP functions which we will call later. We don't have any OpenMP functions in here yet, so actually we don't need it too bad.
We've got our
First thing we do, we have a pragma here that creates a parallel section of code. After this bracket here, after that bracket there, we create threads. So when we print f hello, it is not going to be one thread printing hello. It is going to be a number of threads printing hello. So when we run this, we should see more than one hello. We should see multiple hellos. There is a problem with this code though. It works, but we didn't specify the number of hellos to print. We didn't choose the number of threads. The number of threads in this code is selected by the environment variable, which is an operating system constant. So inside your operating system files, inside your registry or inside your environment variables, there is a number which says how many cores this machine has. That is the number which we will use when we run this program. So in this case, I think it's 16 right now. It might be 32. We're going to find out when I run your codes. Right now, if you try to use G++ to compile this, nothing will happen. But we're going to do something else. When we get to this bracket, all of the threads that we created are destroyed. All of the information that we generated here is destroyed as well, unless we save the data that we produce inside this section to a variable. In this case, we haven't. All we're doing is saying hello many times. Then we return 0. That's the end of our program. Here we only have one thread because all the other threads are destroyed. And life is good. Let's compile it. To compile it, there are a couple of things you need to do.
All we're doing is saying hello many times. Then we return 0. That's the end of our program. Here
That
we only have one
you need to put in.
all other threads are destroyed.
So even if you don't put that in, yeah, I think it will still compile and run, but it might not give you the number of cores that you want. So everyone follow these instructions and run it. G++, our compiler, your file name, -f OpenMP because we're going to be using OpenMP in this code, and the rest of it. When you compile and run this, how many hellos are there?
So everyone follow these instructions.
16.
G++, our compiler, your file name, -f
Oh,
OpenMP
more than 16.
because we're going to be using
32.
in this code.
32 hellos when you run this sucker.
When you compile and run
If you
this,
see,
how many hellos are
oh,
there?
which system are you running on?
16.
You're not running on my computer at all. So this one, 1, 2, 3, 4, 5, 6, 7, 8.
32.
Are you using
32
i7?
hellos when you run this sucker.
I bet you are.
you see-
I'll put money on it.
Oh, which system?
Everyone run it for me.
You're not running on my computer at all. So this
Oh,
one.
sorry, man. You were just out.
4, 5, 6,
Hang on,
7,
everyone. I'm going to go back to make sure Jose gets it.
Are you using i7?
There.
I bet you are. I'll put money on it. Oh. Everyone run it for me.
That's a miracle. Because we didn't
Sorry, man.
we didn't use any
Hang on,
OpenMP
everyone,
functions. I'm
gonna
just
go
getting
back
you
to make
ready
sure
for the
Jose
next
gets
step.
it.
I know you're using my computer because there are a billion threads.
Everyone run it for me.
That's a miracle.
Because
Yep.
we didn't
Yours
we
worked.
didn't use any
It was working here.
functions. I'm just getting
Yeah.
you ready for the next step.
Yep. You wrote "Hello World."
I know you're using my computer. 'cause
That's
there are a billion
perfectly
threads.
acceptable. It still works. You're using one of my machines too? Isn't that one of my machines?
It's working here. Yep.
It's just not your day, is it, man?
That's perfectly acceptable. It still works. You're using one of my machines too.
Show me your code.
Isn't that one of my machines?
Yeah, you spelled parallel wrong.
It's just not your day, is it?
Computers suck, don't they?
If we have a wrong
Show me your code.
Yeah, because the compiler will see the pragma and then say, oh, this pragma doesn't make sense, and just ignore it, which is what happened to you.
Computers suck, don't they? Yeah, because the
Yeah.
compiler will see the
Is that how
pragma
many you got?
and then say, oh, this
You trust
pragma
me,
doesn't
you did.
make sense, and just ignore it.
All right, let's keep going. Let's talk about this for a bit. Everyone got their code working, right? Did yours work, Tria? Excellent. That's how easy it is.
Yeah.
We didn't have to create any special kernels. We don't have to specify blocks or threads. We just type in pragma, OMP, parallel, and we create our threads this way.
Let's talk about this for a bit.
The bug, however, the problem with this approach is that we can't control the number of threads directly. If I want to change the number of threads from 32 to 16, I need to do something with Windows.
Any special kernels. We don't
Oh,
have to
no,
specify
no, no,
blocks
no,
or
no,
threads.
no.
We just type in pragma, OMP,
Please don't
parallel,
restart
and
my
we create
machine.
our threads this way.
Did it
The
just finish
bug,
updating?
However, the problem with this approach is that we
Yeah.
can't control the number of threads directly.
What's your question?
If I want to change the number of threads from 32 to 16, I need to do something with Windows. Oh, no, 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 no.
Yeah, of course.
Please don't.
I have to shut the whole machine down.
Did it just
Yeah.
finish updating? The problem with this approach is that we can't control the number of
On my machine, I'm going to kill you, man. No, I'm just joking. Beats me.
Yeah.
But I mean, no,
I have to shut the whole machine down.
my kids are here. I wasn't doing anything on the weekends. I rode to Mainong on the weekend. You saw my post. I broke the pedal on my bike.
I'm going to kill you, man.
It was a 70-kilometer ride. Yeah. I broke it 62 kilometers in, so the last 18 kilometers were done with 1.5 pedals on my bike.
No.
This stuff only happens to me, I swear.
I
We
rode
ready?
Mainong on the weekend.
Let's continue.
Pedal on my bike.
Let's talk about this.
It was a 70-kilometer ride.
You can use
I broke it 62 kilometers in, so the last 18
just not even one.
were done with 1.5 pedals on my bike. No.
This stuff only happens to me, I swear. We ready? Let's continue. Let's talk about this. You can use
I broke it 62 kilometers in, so the last 18
just not even one.
were done with 1.5 pedals on my bike. This stuff only happens to me, I swear.
We ready? Let's continue. Let's talk about this. You can use just not even one. All right, let's get back to it. In Windows, when you go to Systems, to the Control panel, and you go to the Loading panel, it shows you how many threads you have and how busy each thread is. Have a look on your Windows machines now. Go to the Control panel, please, on Windows.
All right. Let's get back to it.
Task
In
Task
Windows,
Manager,
when you go
sorry.
To Systems, to the control
Right
panel,
click on the bar.
and
Yep.
you go to
Task
the
Manager.
loading panel. It shows you how many threads you have and how busy each thread is. Have a
Oh,
look
it is
on
there,
your Windows
but you
machine.
can't see
Go
it.
to the control panel, please. On Windows. All right. Task Manager, sorry. Right click on the bar. Yep. Task Manager. It shows you how many threads you have and how busy each thread is.
Yep.
Oh, it is there.
Now,
but you can't see
in Windows here, when you open up, do you know how to move? Kids nowadays, man, I swear. Who has trouble finding it? These millenniums, I swear.
Now,
Am I that grumpy old man yet?
when you open up, do you know how to move?
You found it? You found it the long way.
Kids nowadays, man, I swear.
Easily.
Who has
Yeah, it's
trouble
easy to
finding
get
it?
to.
These millenniums, I swear.
And is this a virtual machine?
Am I that
No.
grumpy old man yet? When you open up, you found it?
All right. Your computer is probably telling you that you have more cores than you actually have.
Yeah, it's
The problem is Windows, with Windows and Intel, and any modern Intel chips support hyperthreading. Hyperthreading is the ability for each physical core
Alright.
inside that Intel chip
Your
to
computer
take
is
on
probably
multiple
telling you
threads.
that you
In this
have
case, two
more
threads.
cores than you actually have.
So each physical core can take on 2 threads.
The
In
problem
Windows,
is
when you see
Windows
8 processors there,
with Windows
there aren't
and
probably 8 processors.
Intel,
There are probably
any
4
modern Intel chip
physical
support
processors,
hyperthreading.
and
Hyperthreading is
the other
ability
4
for
are
each
threads
physical core inside
that
the Intel
aren't
chip
real
to
physical
take on
processors.
multiple threads. In this case,
So, in this case, if you see 8, there's probably only 4. When you use OpenMP to do parallel computing,
processors, there are probably 4.
you're probably only going to get a 4 times speed up, even if you only use even if you only use 8 threads, because you don't have 8 physical cores. The cores that you see in Task Manager here, they
In
are
this case,
fake.
if you see 8,
They're not real. They include hyperthreading.
when you use OpenMP,
If you have an AMD
parallel
system, it's a
computing,
little bit different. But my understanding, these are all Intels. At least they all have Intel stickers on them.
even if you only use 8
So these all support
Because you don't
hyperthreading.
have
So not all of these cores are real.
the cores that you see in
If I were to run this code on an
They are
i3,
fake.
it would
They're not
print
real,
4
they include
times.
hyperthreading. If you
But
have
how
an
many
AMD
cores
system,
does an i3 have?
But my understanding, these are
2.
all Intels. At least they all have
i3 supports 2 cores with 4
these all
threads.
support hyperthreading. So
In
not
the
all
environment
of these are
settings,
real.
if you go to an i3 computer and you go to Taskbar, Task Manager in Windows, it will say you have 4 threads, 4 processors, but you only have 2. And here, it's going to print out 4 times, even though it only has 2 cores. Because the environment setting in your system registry is going to say that it supports 4 threads.
Settings, if you go to
Reality only supports 2.
Taskbar, Task Manager in Windows, it will say you have 4.
So we have to be very, very careful.
But you only have 2.
The easiest thing we can do is
Here, it's going to print out 4
choose the
times,
number of threads
even
to
though it
run
only has 2 cores.
in
Because
OpenMP
the
ourselves.
environment setting in your system
Yeah, we can pick
registry
here
is
the
going
number
to
of
say that
threads.
it supports
So we
4
can
threads.
choose. We can control it.
Reality only
We have 2 things we can do. We can either change the environment settings or we can write the code to
So
change
we
it.
have to be very, very careful.
So,
The easiest thing we can
yeah,
do
we know
is
this. This code is the code that we just reviewed. This is where we create and destroy threads. Printf is executed by all of the 32 threads if you run it on my
So
server.
we can choose. We
Piece
can
of cake.
control it. We have 2 things
Next.
we can do. We can either change the
We
environment
create
settings or we
threads
can
at the
write
top
code.
bracket and we destroy the threads at the bottom.
So
There's my sexy
yeah,
arrow.
we know this.
Here we
This
are.
code is the code that we just reviewed. This is where
If
we
you want to
create and
change the
destroy
number of
threads.
threads,
Printf is executed
there are 2
by
things
all
we can do.
32 threads.
We can change the environment variables. Now,
Piece of cake.
if you're using Linux or Unix,
We
this is
create
really
threads
quite
at the
easy to
top
do.
bracket and we destroy the
We
threads
can
at the bottom.
Type
There's my
set
arrow.
OMP num threads and pick a number.
If you want to change
And
the number of
if we
threads,
do that at the command prompt, that will
there
be
are 2
enough.
things we can do.
Please do not
We
do
can
that
change the
on my
environment
terminals.
variables.
I'll find who
Now,
you are and
If
I'll
you're
get you.
using Linux or Unix,
That is a
this
horrible
really
way of
quite
doing it.
easy to do.
Like I just said, we have to be careful
Set.
because
OMP num threads
the environment variable normally takes into
And
account the
if we
maximum
do
number
that
of
at the
threads
command
that
prompt,
your
that will
machine
be enough.
supports. Not
Please
the
do not do
maximum
that
number of
on my
physical
terminals.
cores, but the number
I'll
of
find
physical
who you
threads.
are, and I'll get
So on an old Sandy Bridge i7,
That is a horrible way of doing it.
on the old Sandy Bridge
Like I
i7,
just
we had
said, we
4
have to be
cores and 8
careful.
threads. It will say
Because
OMP num threads 8.
the environment
even
variable
though it should only
takes
be
into
4.
account the maximum number of threads
So
that
we have to take
the
care.
machine supports. Not
But
the
a better
maximum
way,
number of
instead of
physical
changing the
cores.
environment variable and
So on
destroying
an
my
old
computer,
Sandy Bridge i7,
I have a better idea. Let's use
old
our
Sandy Bridge
OpenMP
i7, we had
function
4 cores and
to
8
choose the
threads.
number of threads.
It will say OMP num
Please
threads
write
8,
another code.
even though it should only be 4.
Do not just edit the code that I got you to write just now.
But a better
Please
way,
create a
instead
copy
instead
of the code you
changing the
wrote now
environment variable,
and create a new code
I have a better idea. Let's use
Using
our
this.
OpenMP function to choose the number of threads.
No.
Please write another code. Do not
Yep,
just
they can
edit
bite
the
me.
code
That's
that I
later.
got you to write just now.
Yeah, that has to do with
Please
thread
create a copy of
allocation.
the code you wrote now and create a new code.
That is a variable. That's called thread affinities. Yeah, small steps, Alex.
They can buy that later. Yeah, that has to do with thread allocation. That is a variable. That's called thread affinities.
Yeah.
Yeah, small steps, Alex.
And using MPI run. Yeah, so?
That is a variable. That's called thread affinities. Yeah.
No, it's not strange. No, because you're not using MPI here.
And using MPI run. Yeah, so?
Yeah, isn't that lucky?
So that is just like
Yeah.
okay.
No, it's not strange. No, because you're not using MPI here. Isn't that lucky?
This is a great code because after you've got this code, you can pretty much easily write any GPU code we've discussed so far in the course and finish it quite quickly and make it run. There's only one or two more things after this I need to introduce to you.
This is a great code because after you've got this code,
Take
you
it.
can pretty much easily write any GPU code we've discussed so far in the course.
Hey.
Finish it quite quickly and make it run. There's
Now,
only
do you
one
want
or
to
two
join
more
in?
things after this I need to introduce to
I've
you.
got an idea for you then. Yeah, why don't you,
Take it pretty much
use dev C++, because we can use OpenMP on this machine with this.
now. Do you want
When
to
you
join in?
finish copying that code, come and get me, I'll show you how to compile it.
Yeah, why don't you
Use dev C++, because we can use OpenMP on this machine with this.
now?
When you finish copying that code, come and get me, I'll show you how to compile it. One time I took it into the toilet. Oh, what a life. So, by this time, now that I'm back, everyone here should have a working code. This code should make some sense. What happens in this code? Let's have a look. This code is quite different, and it is much more useful than the previous code we ran. In the previous code, we used the environment variable set and num OMP threads to dictate how many threads we create. This is very dangerous because if you want to change it to run 4 threads, but at the same time someone else has SH'd into that computer and wants to run theirs with 8 and changes the environment variable while you're using it, bad news. So in this code, we use an OpenMP function which allows us to control how many threads to create. OMP set num threads. Now, the reason why people enjoy using OpenMP so much is because this is a pretty clear and easy to understand function. OpenMP set the number of threads. I don't need to explain too badly because it should be pretty transparent. In this case, P was an integer which was 4. So when we ran our code, we should see that 4 threads ran. We should see the same message printed 4 times, but it's not exactly the same message. And this is very important for us to know. This is our message. Now, let's see. Here we wrote, hello from thread something, and we use TID here. This is not an easy thing because in CUDA, each thread knew its ID because there was an environment variable called thread idx.x. You guys remember that? In CUDA, each thread knew its ID because there is a special variable in CUDA that allows each thread to know what its ID is. There is no such variable in OpenMP. However, there is a function which allows us to compute what that thread is. So here we have a thread ID, TID, and we compute the TID by using this function OpenMP getThreadNum, which is getThreadNumber. So here we're using OpenMP. We create our threads. As soon as we create our threads, the very first job each thread has is to compute what its thread is, what its ID is. It doesn't come included in a variable like CUDA. We have to actually compute what it is. Now, so here we're using OpenMP. Look at the code I'm writing here. As soon as we create I want to talk to you about something. Each thread has is to compute what its thread is, what its ID is. It doesn't come included in a variable like CUDA. We have to parallel Jamba. Now, after this, I've got this private. Look at the code I'm writing here. As soon as we create, I want to talk to you about something. TID. You know, the best way to learn is to make mistakes, right? So from time to time, I will make you make a mistake on purpose. Sometimes I'll tell you, sometimes I won't. Today is one very special time where I'm going to make you make a mistake, but I'm going to tell you it is a mistake before you make it. I want you to delete that in your code and compile and run your code one more time and see what happens. Sometimes I'll tell you, sometimes I won't. I want you to delete the section of code that says private TID. So in the pragma OMP parallel private TID line, I want you to remove private TID. Then I want you to compile and run it again. I want you to delete the section of code that says private TID. Huh? So in the pragma OMP parallel private you forgot to add it in, man. I'm so glad that I designed my courses so that people make mistakes without me having to tell them. Yeah, it's random. But actually, it seems to work pretty well. Huh? Yeah. You forgot to add it in, man. I'm so glad that I designed my courses so that people make mistakes without me having to tell them. That's all right. Some of you may have discovered that the result didn't change. This is because you are very fortunate. It is not because of anything except luck and because of the way I've amended the system. I want you to write something for me. Replace that private with shared. That the result didn't change.
This is because
and see what happens.
you are very fortunate. It is not because of anything except luck and because of the way I admitted the system. I want you to write something for me. Replace that private with shared. This is because
And see what happens.
you are very fortunate. It is not because of anything except luck and because of the way I admitted the system. I want you to write something for me. Replace that private with shared.
I know. Okay, calm down.
No, what I mean is like, I thought that was the reason that it's random, but it's not. Before I didn't use it, I forgot.
Oh no, I mean, the random order is just because one core is faster than the other one.
I know. Calm down.
Now, some of you are probably discovering that, well, it really depends on what system you're running on.
Oh no,
The
random
outcome of
order
this
is
test.
because one core is faster than the other one.
There is a big difference between writing private TID and shared TID. And we have to think about what these two actually mean. Private TID, TID is an integer. It is a variable in our code.
Depends on what system you're running on.
When we create something as shared or private, we're changing the scope of the variable. So let's have a look at what that is. If I were to make TID shared, that tells us that there is one TID in memory, just one,
when we create something
and
as
all
shared
of the
or private,
threads have
we're
access
changing
to the
the
same
scope of
variable,
So let's have a look at what that is.
and they're going to queue around it
If I were to
and
make
line up,
TID
and
shared,
they're going to wait for it to be
That
free
tells
before they
us
use
that
it. It's a little bit different to
there is
GPU because
one
GPU
TID
won't
in
wait,
memory,
but OpenMP
one.
will, depending on your machine.
and all of the threads have access
Each
to
of
the
these
same
threads is
variable,
going to have access to it from thread 0 up to
they're
P
going
minus
queue
1,
around it,
and they're all going to try and write to this.
line up,
When we
they're going to wait for it to be free
do this,
before they
if
use
this
it.
is shared,
It's a little bit different
or
to
we
GPU.
don't write anything here,
But
if we don't write anything by default, it is shared.
depending on your machine.
When we run
Each
this,
of these threads
all
is
the threads are
have
going to
access
try
it
to write over
from
TID.
thread 0 up to P minus 1.
That means that we are going to have data racing.
When we
Doesn't mean that our code will not work,
or we
but
don't write
let me
anything
give you a hint
if we don't
about
write
what
anything
actually
by
happens.
default, it is shared. When we run this, all
In
the
today's
threads are going
example,
to
we
try to
have
write
a simple OpenMP code with 4 threads.
That means
And
that we are
by
going to
making
have
TID shared
data
or
racing.
not writing down that it's private, it
Doesn't mean
worked,
that our
right?
code will not work. But
It is a
let me
miracle.
give you a hint about what
As
actually
soon as you
happens.
write a scientific computing program, it is going to stop working.
In today's example,
and your
we have
code
a
is going to
simple
fail.
OpenMP code with
I
4
promise you
threads.
this.
And by making TID
We
shared,
really
not
need
writing down that it's
TID
private,
not to be shared. How can TID be shared?
it is a
Every
miracle.
thread should have its own name, right?
As soon as
Makes
you write
sense.
a scientific computing
What is
program,
happening in your codes now, if you make it
it's going to
shared,
stop working.
is that by some miracle,
Fail.
each thread is completing just in time to write its own value down correctly in that TID,
How can TID
and we're
be
using
shared?
blocking to make sure everything
Every
still
thread
works.
should have its own
But it
name.
is luck.
As soon as
If you
makes
try
sense.
any large
What is
computation with
happening in
many
your
threads,
codes now,
bad
if you
things will
make it
happen if
shared,
you don't
is
control
that by
TID
some
properly.
miracle,
So we want to
each
make
thread is
TID private.
completing just in
When we
time
make
to write
TID
its own
private,
value down correctly in that TID,
we create 4
and
copies.
we're using blocking to make sure everything still works.
So
But
I
it
know
is
in
luck.
our code we say
If you
int
try
TID.
any large combination
Kanske det
of
var
many
men
threads,
geo
bad
ige
things
int.
will happen if you don't control
But as a matter of fact, if
So
we
we
say
want to make
that the number of
TID
OpenMP
private.
threads is 4,
When we make TID
each
private,
thread will have its own TID.
we create 4 copies.
So how many TIDs will
So
there actually be
I
in
know
memory?
in our code we say int TID.
5.
Kanske det var men geo ige int.
If there are
But
4
as a matter of
OpenMP
fact,
threads,
if we
each
say that the
OpenMP
number
thread
of
has its
OpenMP
own
threads
TID
is
variable,
4, each thread will have its
plus
own TID.
the first TID thread,
So how many TIDs?
which is its own and separate from the others. So when we run our program, we have int
There are
TID at the
4
beginning.
OpenMP
That's the
threads.
first address in
Each
memory.
OpenMP
By
thread
setting
has
TID
its
to be
own
private,
TID variable.
we create, in this case, because we have 4 OpenMP
First
threads, we
TID.
create 4 copies in memory.
Which is
Now,
its own
in
and separate
GPU,
from the others.
if you want to do this crazy kind of work,
So
we
when
need to
run our
manually
program,
allocate those 4
we
thread
have
IDs,
TID
right?
at the beginning,
One
that's
mer
the first
digital
address in
när
memory.
kude med allt det går
By
så.
setting TID to
But
be private,
in OpenMP, we don't. we don't have to allocate space in memory for all of those. OpenMP does it for us automatically.
If you want to do this crazy kind of work,
Does it work all the time?
manually allocate
No.
4 thread IDs, right?
We have to be very careful with OpenMP because OpenMP, all of the hard work is done by the compiler.
We don't have to
Sometimes the
allocate
compiler makes
space in memory
mistakes,
for all of those.
and we
OpenMP
forgive it.
does
That's
for
okay.
us
That's life.
automatically.
So, OpenMP will automatically help you create the space in memory for those 4 extra TIDs.
OpenMP because OpenMP, all of the hard
Wonder
work
if we
is
can
done
try
by
an
the compiler.
experiment now.
Sometimes the compiler makes mistakes. And we forgive
I'm
it.
going to log into the server, and we're going to play a game.
So, OpenMP will automatically help you create the space in memory. For
Isn't
those
that what the
4
guy in Saw
extra
said?
TIDs.
Yeah, it didn't mean it to be scary.
Wonder if we can try an experiment now. I'm going to log into the server.
Well, I tell you what, that's
I'm gonna play a
scary.
game.
The ANSYS overview.
Isn't that what the guy in Saw said? Yeah, it didn't mean it to be scary.
Oh, and now we need to play this game again. Default foreground is
Well, I tell you
white.
what, that's scary. The ANSYS overview.
Default, hang on, default foreground is black. My bad.
Isn't that what the guy in Saw said?
Default background is white.
Oh,
That'll do.
and now we need to play
And
this
we need to
game
change the
again.
font.
Default foreground is white. Default, hang on,
Which one did we like to
foreground
change
is
it to?
black. My bad. Default background is white. Oh, that'll do.
Which one?
And we need to change the font.
Huh? Digama. Let's try that.
Which one did we like to change it to?
I hate having to save these every week.
Which one?
Oh wow, look at that. Every week it's always the same. The Chinese gets me.
Let's try that. I hate having to save these every week. Oh wow, look at that. Every week it's always the same. The Chinese gets me.
Oh, look, this was already one. Excellent. Perfect. I'm changing that. I know it's yellow. We have to find a way to save the settings every week so that I don't have to redo it every week.
Excellent.
Ah,
I'm changing that. I know it's yellow. We have to find a way to save the settings every week so that I don't have to redo it every week. Excellent.
how do I set the number of OpenMP threads again? People, I need your help. How do I change the number of OpenMP threads? What's the function name? That?
How do I set the number of OpenMP threads again?
Let's set it to 4.
People, I need your help. How do I change the number of OpenMP threads? What's the function name?
Now I know that you guys can't read that,
That?
so let me highlight it.
Let's set it to 4.
Oh, because private is a separate keyword in C. Let's talk about this code that I've written here for a second. I know it's very difficult to read this yellow text,
Highlight it.
but I want you to use your superhuman powers. I'll tell you what it says. It says TID equals %D/n. So I'm asking it to print the value of TID here. Now, I set
Let's talk about
int
this code that I've
TID
written
equals
here for a
2 here.
I know
What
it's
will
very
each
difficult
thread
to read
print?
This yellow text, but I want you to use your superhuman
Will it print
powers. I'll tell you what
TID
it says. It
equals
says TID
2
equals
4 times?
%D/n. So I'm asking
Well,
it
let's
to
find out.
print the
Let's see
value
what
of
happens when I
TID
run
here.
this.
Now, I set int TID equals 2 here. What will each thread print?
Oh,
Will it
typical.
print TID equals 2 4 times? Oh, well, let's find out. Let's see what happens when I run this.
Oh, I didn't change it. Hang on. Tell me about it. Oh, I didn't change it. Hang on. Tell me about it. Hang on. Yellow. Pick a color that's better than yellow. Purple. Yellow bold. Hot pink. There you go. What other color sucked? Green? Yellow. Green is now red. Purple. Green bold. You're redder. Yellow bold. Hot pink. There you go. What other color sucked? Green? Green is now red. It didn't do the backgrounds. Green bold. You're redder. Yellow bold. Hot pink. There you go. What other color sucked? Green? Green is now This is going to drive me crazy. It didn't do the backgrounds. Hang on. It's going to drive me crazy. I'm saving. Hang on. Better. I'm saving. Oh, that light blue is going to annoy me. Better. It doesn't know what TID is. Yeah, thank you, man. Oh, that light blue is going to annoy me. I'll tell you what. It doesn't know what TID is. I'll tell you what. Is everything right there? Is everything right there? Well, that only took about half an hour to do. What happened here? I set int TID equals 4. I did, right? Did I make a mistake in my code? Then when I run my thing, I've got 4 different threads printing what TID is equal to. Meu eget print Deutebar. They all print some crap number. 32702, I don't even know what that is. What happens if I run it twice? Then when I run my thing, I've got a new bug. In this case, we have a bug which changes every time we run the program, which means that we have an error in our parallelization. In this case, what is wrong? The variable TID, we have 4 threads here. We have 5 copies. The first copy, TID, is 4, but the other 4 that are created by OpenMP when we create our 4 threads, I didn't set those values. Did you set them? No.
variable TID.
That's what they are.
We have 4 threads
Each
here.
thread has its own
We have 5
TID,
copies.
but we never asked the computer to compute what TID was.
But
Let's
the
have a look.
other 4 that are created by opening
Here I
these
set
up,
int
we
TID
get our
equals
4
4.
threads.
I set the number of
I
threads.
didn't set those values.
Let's do something fun.
No.
Oh no 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 no
That's
no
what
no
they
no
are.
no no no.
Each thread has its own TID.
100.
But we never asked the computer to compute what TID was.
Let's do it.
Let's have a look. Here I set int TID equals 4. I set the number of threads.
There's that 32676 again. No, it's a new number. We've never seen that number before. What is that number there? It's rubbish.
Let's do it.
This is garbage. This is one of your numbers that you saved in my memory, but didn't remove because you forgot to use 3.
Again. No, it's a new number.
Oh, I don't know. Maybe it is, maybe it's just leftover rubbish that wasn't collected.
What is that number there? It's
So
rubbish.
what is the drama here? In this case, in this code, we never
This is one of your
told
numbers
each
that
thread
you saved in
what
my
its
memory,
TID was.
but didn't remove
If I
because
set
you
it equal to
forgot
2, well, that's a piece of cake.
I don't know. Maybe it is.
It's
maybe
2.
It's just leftover rubbish that wasn't.
But the scope of that variable is unique
So
for
what is the drama
TID.
here?
So by making
this
a
case, in
variable
this code,
private,
we never
we create many copies. In this case, we have 100 threads, which means there are 101 TID variables. Each one has its own.
It's 2. But the scope of that variable is unique for TID. So by making a variable private, we create many copies. In this case, we have
What is that going to
100
give me?
which means there are 101 TID variables. Each one has its own.
No errors, man. 4. Yeah. So these TIDs
What is that going to give you?
only exist for these threads. Each of those 100 threads has its own TID. The first TID,
No errors.
that is valid within the scope of the entire main program. That one, no thread touches. So if we have 4 threads, we have 5 TID variables.
These
The first
TIDs
TID,
only
in this case, we
exist
set
for
to
these
4.
threads.
The last
Each of
TID,
those
if
100
we
threads
set
has its own
to 4
TID.
threads, let's
The
do that.
first TID,
We
that
set to
is
2
valid
here.
for the scope of the entire main program.
But whatever changes
That
we
one
make to
no thread
TID inside that pragma
So if
do
we have
not
4
go back
threads,
to the
we have
original
5
TID because
variables.
by making
First
this
TID,
variable
in
private,
this case we set
each
to
thread
4.
has its own TID.
Last TID,
All
we set
computations done to that variable then become its own.
We set to 2.
They are saved within that thread's own variable. But as soon as the threads are destroyed,
inside that pragma,
all of the variables, all of the TID spaces in memory are
making this
are
variable private,
gone.
each thread has its own
You don't get to
TID.
see them anymore.
All computations done to that
So what does that
variable
mean for
then
us?
become its own.
Rugo
They-
woman yao
they
yong
are
open and
saved
peep
within
hawigi
that
ji shuan.
thread's own variable. But as
Woman
soon as the
buke
threads
tremble
are
yong
destroyed,
private.
all of the variables,
Right?
all of the TID
Because if
spaces in
all of the
memory
variables are private, that means that, well, let me think about what that means. It means that the work
So what does that mean
performed
for
by
us?
every thread is destroyed at the end of the
Rugo woman yao
parallel
yong open and
computation.
peep hawigi ji shuan.
So,
Woman buke tremble yong
is there an
private.
earthquake?
Right? Because if all of
Did
the
you feel it?
variables are private,
Just a little rumble?
that means that,
Is it the wind?
let me think about what that means. It means
Yeah.
that
Anyway,
the
it-
work performed by every
oh,
thread
I
is
felt something.
destroyed at the end of the
Yeah.
parallel computation.
You Taiwanese don't count because you guys are insensitive to earthquakes. You've been having them since you were born. So TID has its own variable. If we make this shared,
Anyway,
what's going to happen?
I felt something. Yeah. You Taiwanese don't count because you guys are insensitive to earthquakes. You've been having
By
them
making it shared, you do not create unique copies for each thread.
So TID.
By making a variable
has its
shared,
own
there is only
variable.
one
If we
copy
make
of
this
TID,
shared,
and whatever you do to it inside
What's
each
gonna
thread is going to be, it's going to remember. So let's play a game. TID equals, what is it, OpenMP,
unique copies for each
get, thread,
variable shared,
num?
there is only one copy of TID, and whatever you do to it inside each thread is going to be. It's
Who
going
can
to
tell me
remember.
what TID will be at the
So
end?
let's play a game. TID equals, what is it? OpenMP,
One? 1,
get,
1, 1,
thread,
1, 0, 1, 0, 1, 0, 0, 0, 1. Come on, 2. Where are you?
tell me.
3. There's 3.
Will be at the end.
We can't control which threads are faster or slower. So just like GPU parallel computing, we have no way of controlling which threads are performed first. So in this case, we can see most of the time it was thread 0 that was the slowest. That damn lazy 0. But sometimes thread 1 is, sometimes thread 3 is, Daoshinzai thread 2 is never the last one. Oh, there he is, yep. So in this case, we can see most of the time it was thread 0 that was the slowest. That damn lazy 0. But sometimes thread 1 is, sometimes thread 3 is. Here? Thread 2 yep. Is never the last one. Because we're, there he is, one of the jobs is printing, the other one is reporting the final result. So between printing the result and destroying the threads and then getting there, something else might have happened. Show me. Here? Yep. Because we're, one of the jobs is printing, the other one is reporting. Of course you can. So of course you can define a variable in there. The result and destroying the threads and then getting there, something else might have happened. Well, it's automatically private if you create a variable in there. I'll show you. Let's have a look. Yeah. Of course you can. Of course you can define a variable in there. Int. Pick a variable name. Thank you. Excellent. And let's set it equal to 2. Yay. And we'll multiply that. Win. Int. This will work. Thank you. Excellent. And let's set it equal to 2. Everything's fine? Yay. And we'll multiply. You guys should be able to tell me what happens now. Win. What happens if I write this? This will work. Will this compile? No, it will not. This won't compile. The scope of the variable x is limited to between these two brackets. This is C programming. This has nothing to do with parallel computing. This is just regular C, C++ programming rules. If we create a variable between these two brackets, that x only exists between these two brackets. If you don't believe me, let's compile it. Is limited to between these two brackets. This is C. X was not declared in this scope. And then you're going to say, it was declared, but it wasn't declared in that scope. Let's play another game. If you don't believe me, let's compile it. What's it going to say? X was not declared in this scope. I put int x equal to 4 out here. So there now are two x's. There are x's in here, and there's an x out there. The question I put to you guys, will it multiply these by 2 or will it multiply by 4? That's right. Equal to 4 out here. So there now are two x's. There are x's in here, and there's an x out there. It's still multiplied by 2. But the x outside of our parallel scope is still 4. There are two different, well actually there are more than 2. In this case we create 4 threads. How many x's do we create? 4. There are actually 5. We start with x, and then for each OpenMP thread we create a new x variable. So these 4 threads each have their own x. So you can see here, we don't need to define x out here and then make it private. There are actually 5. It is automatically private. We start with x, and then but we have to define what it is. Otherwise, you don't know. So in here we use this x, out here we use this x. This one here, down here. This has nothing to do with parallel computing. This is all about C programming. I know that your teacher for the Introduction to Computer subject did teach you about this stuff. I'm pretty confident he did, because I know him as pretty smart and pretty handsome and tall, and is pretty good at teaching computers. But that's okay, because it's okay to forget about these things. X is a local scope, only exists between these two brackets, otherwise we're using these. I'm pretty confident he did, because I know him as pretty smart and pretty handsome and tall,
and it's pretty good at teaching computers.
Oh,
But that's okay.
Oh, I
because
need to swap
it's
it out.
okay to forget about these things. X is a local scope, only exists between these two brackets.
so the flow
otherwise
chart. Let's have a look.
we're using these.
This is where we create a private TID. TID has to be private, so each thread has its own copy. This is actually a little bit inaccurate. When we start the calculation, we have one TID. There should be another space here. Then when we create our threads, we
So the
create
flow
4
chart.
threads here. We
Let's
can
have
see
a
there are 4 lines
This
here,
is
which
where we create
indicate to
a
us that we're
private
creating
TID.
multiple
TID
threads.
has to be private, so each thread has its own copy.
There are 4 new TIDs
This
here.
is actually a little bit inaccurate.
This TID still
Start the calculation,
exists
we have
in
one
a separate
TID.
part of memory.
Should be another space here.
But when we create
Then
these
when we
4 private
create our
TIDs,
threads, we
by
create
declaring
4
them as
threads here. We can
private,
see there are 4
we no longer have control over their value. We need to set the value of TID, otherwise it just takes the
There are
garbage
4
which is
new
in that memory
TIDs.
section when we allocate TID
This TID
for each thread.
still exists in a separate part.
When we finish our computation and
But
all of
when
our
we
threads are
create these
collected,
4 private
we
TIDs,
only have one
by
TID
declaring
remaining, the
them as
original
private,
TID.
we no
It has
longer
whatever
have
value
control
it
over
had
their
before it
value.
went
We
in.
need to set the value of TID,
Any
otherwise
information allocated to these TIDs, that's different values. Those are in different locations. Once our threads are collected, all of that
when
data
we
is
finish
destroyed.
our
It's lost
computation
forever.
and all of our threads are collected,
So this is important
we
because
only
when
have
we
one
perform
TID,
calculations in
the original
OpenMP,
TID.
the results
It has
of your
whatever value
computation
it
from
had
each
before
thread
it went in.
must be saved in a shared variable.
Any information
If you
allocated
put
to
them
these
in
TIDs,
private
that's
variables,
different values.
they will be
Those are
destroyed
different
after the threads are
locations.
destroyed.
Once our threads are collected, all of that data is destroyed. It's lost forever.
What are the drawbacks?
So this is important because when we perform calculations in OpenMP,
In our computation work here, we love to create arrays, don't we? We like to say things like get new pens. Merry Christmas.
What are the drawbacks? In our computation work here, we love to create arrays, don't we? We like to say things like get new pens. Merry Christmas.
If we've got an array, a 1D array, containing n variables, let's say we want to perform our computations using array A. If A is shared, how many A's are we creating?
If
There's
we've
one.
got an array, a 1D
If I
array
make the variable A
containing
private,
n variables,
how many arrays are we creating?
let's say
However
we
many
want to
threads
perform
plus
our
1.
computations using array A.
If we have a finite element calculation
If A
and
is
we
shared,
have 1 million
how
elements
many A's
and
are we
A is
creating?
private,
Just one.
congratulations, you just
If I
created
make the variable A
however
private,
many threads times 1 million
how many
elements.
arrays are we creating?
So we must be careful.
However
If
many
we have a
threads
large
plus
array, making it private
a
will mean
finite
you
element
use a
calculation,
lot of RAM
And we have 1 million
because it is
elements,
going to create
and A is
space for
private.
all of those private variables.
Congratulations, you just
It is
created
not a good idea.
however many
Most of
threads
the
times
time in
1
our
million.
engineering calculations, our large solution variables are
So
shared.
we must be careful. If we
Only
have a
small
large
things are
array,
private.
making it private will mean you
Any
use
variable
a
made
lot
private will be destroyed
because it is going to create
when the
space
threads are
for all
destroyed,
threads.
and it will be empty after thread
It is not a
creation,
good idea.
even if the variable had data inside it before threads were created.
Variables are
So we can see in the example we just said, we said int TID equals 2, then I make TID
Any
private,
variable made private will be
but each
destroyed
thread tells me TID is rubbish.
when the threads are
TID is 0
and
or
it
some
will be
garbage.
empty after thread creation.
So we must be careful.
Even if the variable
Any
had
variable
data
you make
inside it
private
before
must be defined or redefined
So we
after
can see
thread
in the
creation.
example we
You
just
must
said,
give
we
it a
said
value.
TID equals 2, then I make
Now,
TID
believe it or
private,
not,
but
you
each
guys
thread
have got
tells me
all the
TID
tools
is
you need
rubbish.
to make pretty much
TID is
any
0 or
parallel
some garbage.
program
So we must
using
be careful.
OpenMP at least.
Any variable you make private must be defined or
Let's have a look.
redefined after thread creation.
Private variables, here we create TID, make it private like that. You already
Now,
know that.
believe it or not,
We can't see those.
you guys have got all the tools you need
Can we see?
to
You
make
can't
pretty
read that
much
at all.
any parallel program
That
using
sucks.
OpenMP at least.
Forget it.
Let's
I'll
have a
put
look.
these online. You can read them at a later date.
Private variables,
These
here we
two
create
codes that
TID,
you can't
make it
read
private
here
like that.
are
You
two
already know that.
codes that contain bugs.
Can't see those.
Each of the codes that you can't read here has a bug. When you run it, it compiles, but it runs incorrectly.
Forget it.
If I remember correctly, the left code is bugged because TID is not
These
made
two codes
private.
that you can't read
And the right code
codes that contain bugs.
is bugged for
each
some
of the
other
codes
reason,
that you can't read here has
you guys can read about it online in the
When you
notes
run it,
because there's
it-
no
it
way I can read
compiles,
that now.
but it runs incorrectly.
Ah,
If I remember
Today's
correctly,
tutorial
the left
exercise.
code is bugged because
today's
the code is
tutorial.
private.
Blah, 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 blah.
And the right code
I know that you guys are used to having horrible
It's
tutorial
bugged.
exercises.
for some other
Over the last 10 weeks,
you guys can read
we've
about
gone
it
from
online.
doing baby exercises
There's
at the
no way I
beginning
can read that.
to doing CG on GPU.
Ah.
CG on GPU for final element is about as tough as it gets. It is enough to get a master degree.
I know that
It
you
is
guys
definitely
are used
not
to
enough to
having
get a PhD,
horrible
sorry
tutorial
people.
exercises. Over the
It's
last
not that easy.
10 weeks, we've
But
gone from doing baby
Today's
exercises
exercise, because it is the first OpenMP class, I get to give you guys another baby exercise.
element
Now this has pros and cons. Pros are,
It is enough
to
get a
finish
master's
today's
degree.
exercise takes all of
It is
about 2
definitely not
minutes.
enough to get a PhD, sorry people.
The pro is, if you finish in 2
But
minutes, that means you have more
Today's
time to work
exercise,
on the
because it is
major
the first
assignment.
OpenMP class, I get to give
So
you
that's
guys
what I
another
would
baby
advise you do.
exercise.
But
Now
first,
this has pros and cons.
you remember what we were doing over
Pros
there?
are, to finish
I
today's
was
exercise
mucking
takes
around with
all of about 2
OpenMP,
minutes.
trying making things private, trying making them shared, trying setting new variables,
If you finish
giving
in
them
2
different
minutes, that
variables,
means you
trying
have more time
different
to work
scoped variables. By playing like this,
So
I'm
that's
showing
what
you
I would
methods
advise
for
you do.
learning
But
OpenMP.
first,
I want you to play around with it. Do not destroy my computer, but play. Try creating different numbers of threads. If you want, you can create 10,000 threads. My machine can handle it easily,
playing like this
but it won't like you.
for learning OpenMP.
I think it will remember you and it won't forget.
Play around with it.
Today's tutorial exercise is an easy one. Today's tutorial exercise is a moving filter.
Try creating
Now, if you guys have done experimental work before,
10,000,
surely you're in sort of experiment, huh? Have you guys got experiments?
but it won't
Maybe
like
your professor has given you an experimental rig and you're taking experimental measurements.
Today's tutorial exercise
When you do
is an easy one.
experiments,
Today's tutorial exercise is a moving filter. Now, if you guys have done experimental work before, surely you're sort of experiment, huh? Have you guys got experiments?
let's say you're measuring pressure.
Maybe your professor has given you
and
an
time.
experimental rig and you're taking experimental measurements. When you do experiments,
What does your data look like? Let's say you know what the answer should be. Let's say you know the answer should be this.
let's say you're measuring
But
pressure
when you run your experiments,
and time.
you get not that. You get
What does
this
your data
filth.
look like? Let's say you know what the answer should be. Let's say you know the answer should be this.
there's the actual solution we want, plus
When you run your
what we call
experiments,
noise.
you get
So here we have
Not
noise, signal noise.
get
Where does that noise come from?
this filth.
It might come from the experiment. It might come from the amplification of the signal coming from the transducer. Often comes from
There's
the amp.
actual solution
Because we have to
you want.
amplify the signal we get, because half the time these pressure transducers produce a very small
So here we
voltage.
have
They all work by creating voltage when you apply pressure.
Where does that
We
noise
have to
come from?
amplify that, and then we have to
Might
read
come
it
from
into a
experiments,
machine, maybe a
might come from the
Texas
amplification of the
Instruments
signal coming from the
reader
transducer.
or something like that to get the
Or it
data.
often comes from the amp.
Man, that pen
We have to
stank.
amplify the signal
Anyway,
because half the time these pressure
we have to
transducers
process this. This is not acceptable
They all
results.
work by
If you
creating
give this
voltage
graph to your
by
professor, he's going to
We
execute
have
you,
to amplify that.
because we know the answer is the red line.
Machine may be a
That's not.
Texas
What is this green stuff? Don't worry, your professor knows about noise, so he's not going to kill you.
man that.
But we have to process this.
Anyway, we have to
The average NTU student is probably going to look at this, or NTKU student is going to look at this, and then he's going to perform a Fourier transform on
because
this.
we know the answer is the red line.
Yeah,
That's not.
have fun with that.
What is this green stuff? Don't
The
worry.
noise operates at one frequency, and then you've got the underlying red frequency. You'll pick that up, sure, absolutely.
The
But
average
we actually
NTU
want to see
student
what that
probably
line
gonna
is,
look at this
which
way.
means we have to filter it first.
It's going to perform a Fourier.
This is the algorithm for a moving boxcar filter.
Yeah.
The filter is easy.
Have fun with that. The noise operates at one frequency, and then you've got the.
The endpoints are special points, but let's take an inside point.
But we actually want to.
Let's say we measure
which means
point
we
A,
have to filter it first.
point B, and point
This is
C.
the algorithm for a moving boxcar
Make that
filter.
C bigger.
The filter is easy.
And I want to evaluate a smooth value for
The
B.
endpoints are special
Let's
points.
say I want to find a
So
way
let's
to
take an
remove this
inside point.
noise and find a
Let's
better
say we
value for
measure
B, which I'll
point
give
A,
here.
point
In which
B,
case, I'm going to say B
C,
is equal to, well, let's see, one good way of smoothing
And
this
I
data
want
is to say, let's make the value at B here the average of A, B, and C.
Let's
Just
say
look
I
to the
want
left,
find a way
look to
to
the right,
this
look at
way
me,
and
find the average.
better value for B
That's
is
smoothing.
gift here.
This is like actually
In which case,
adding
I'm going to say
dissipation,
B
right?
is equal
So-
to, well, let's see, one good way of smoothing this data is to say, let's make the value at B
We take
here,
the average.
the average of
1
B
over 3.
and C.
Now,
Just look to the left, look to the right, look at me, find the average.
we can actually extend the range
This is like
if we want to.
actually adding
If I
dissipation.
want, I can say maybe the new value at B should take into account the value 2 spots to the left and the value 2 spots to the right. Maybe I need to weight the different points differently. This is all a different type of
We can
filtration
actually extend the
computations.
range.
Today,
If I want to.
all I want you to do
If I want, I
is
can
find
say
the average
maybe the new
of the
value at
left,
B
the right,
should
and the
take
center.
into account the value
So,
2 spots to the left,
here's the
value
algorithm.
2 spots to the right.
For each
Maybe
point,
I need to weight
you're going to compute
differently.
the average
All
of
different type of filtration
它自己加右边加左边，
Today,
最左边是特别的。
is find the average
The left
of
is
the left,
special.
the right, and the center.
At the leftmost point,
Here's the
its
algorithm.
new value will be the average of this point and this point,
You're going to compute
because it only has access to
the
2
average
points.
of 它自己
So at the
加
leftmost point here,
左边
let's call that A and B
最左边
there,
是特别的
the new value at A is going to be
The left
half of
is
A plus B.
special.
At the right end,
At the leftmost
一样，它只有办法看到两个点，它自己还有左边的，所以最右手边的是 half of the left one
So at
plus
the
itself.
leftmost point here,
All of the others
call that A and
are the average of the center, take away the left, or plus the left plus the right.
at the right end,
Piece of cake.
一样，它只有办法看到两个点。
When you
它自己
write your
还有
code,
左边的所以最右
how are you
手
going to know if the code is working or not? It's quite
the
simple.
left one plus itself.
I've provided
All
data
of
for
the
you.
others
So here I've given you an
center,
array.
take away
A.
the left or plus the
A contains our signal.
piece of cake.
Yes, it's just a small, come on man. 1, 2, 3, 4, 5, 6, 7, 8, 9,
How are you
10
going to know
elements.
if
You
the
can
code
suck
is
it up for
working or
5
not?
minutes.
It's quite simple. I've
Copy
provided
A.
data for you.
The reason being is because if you go through and calculate these by hand, what is the average of 0.7060 plus 0.0318? I'll give you a clue.
1, 2, 3,
It's that.
4, 5, 6, 7, 8, 9, 10 elements. We can
The average of this point plus this point plus this point is that point.
The reason being is
You
because
can
if you
use
go through
this
and
array
calculate
to
these by
test to
hand,
see if your code
what
is
is the
working.
average
That's
of
why I'm giving you this data.
0.7060 plus
So the original data is the blue point. You can see it's bouncing all around, all over the shop. After one pass,
the average
we
of
get the
this
red
point
line,
plus this point plus this point.
which is smoother than the blue line. That's the mission for filtration. We're trying to remove some of the finer frequencies.
That's why I'm giving you
Doing
this data.
experiments this way, by taking experimental data and then filtering like this,
See, it's bouncing
it is
all
important
around,
for me to
all
say
over
that
the
you
shop.
could be losing essential
one
physical
pass,
information from the problem.
We get
There
the
might be actual physical turbulence that occurs on this scale of time that you're losing by doing this processing.
We're trying to
But
improve
you are able to capture the long time
doing
features
experiments this
of the
way by
experiment
taking
more carefully.
experimental data and then
Filtering is something that we need to do.
for me to say that you could be losing.
I want you to do today's work in 2 parts.
There might be
Digger,
actual physical turbulence
write
that
a
occurs
single
on this scale of
CPU
time
code
that you're losing by doing this
to
process.
process this array A.
You are able to
So this array has 10 elements. Using one core,
experiment more carefully.
go through each of these elements and calculate the new average, the new moving average. Then, once you've checked A is the original array, this is the filtered array A. Once your values match mine,
To process this array A.
use
So
2
this array
OpenMP
has 10
threads.
elements. Using
How are
one
you going to
core,
parallelize this work?
go through each of these elements and calculate
It's
the
your
new
core.
average, the new moving
You've
average.
got 10 elements in
Then
your array.
once you've checked
Maybe element
A is the
0,
original array,
3,
this is the
5,
filtered
7,
array
9
A.
will be thread
Once
0.
your values match
1,
mine,
3, sorry, 0,
use two OpenMP threads.
2, 4, 6, 8
How are you
will
going to
be
parallelize
thread
this?
0, and maybe 1, 3, 5, 7, 9 will
It's
be
your
thread
core.
1. That's a stupid
You've
way.
got 10 elements in your
Maybe
array.
thread 0, 1, 2,
Maybe
3, 4 will
element
be
0,
thread 1
3,
in
5, 7,
OpenMP,
9 will be
and
thread
5, 6,
0.
7, 8, 9
1,
will be thread 2,
sorry,
which would be more like the way we taught you in GPU. You take your array, split it into 2 parts.
will be thread 0.
How do we do
1,
this?
3, 5, 7, 9 will be
Exactly the same way we did in GPU. Create 2 OpenMP threads.
1, 2, 3, 4 will be
Calculate an index using the local thread ID plus you have to move the index along by 5, and then the rest is identical to GPU. So today you should have 2 separate codes. One is a CPU code that does that filtering for
create 2
for
OpenMP
10 elements, Then
calculate the index.
open MP using two threads doing the same work.
Thread ID
你的
plus
结果应该是一样. Your answer should be the same.
by 5,
Give you a clue.
and then the rest is identical
A.
to GPU.
Is that shared or
So
private?
today you should have two separate codes. One is the CPU
Shared.
code that does that filtering for
If you make it private, all the values are destroyed.
then open
AS, is that shared or private?
doing the same work. 你的结果
Shared.
是一样. Your answer should be
If you make it private, it's destroyed when you finish your computation. So A is shared.
is that
AS
shared or
is
private?
shared. The thread ID will be private.
Shared.
You will have a
you
new
make it
variable,
private, all the
int
values
index,
are
which
destroyed.
controls which part of the array your
AS, is
each
that
thread
shared
is
or private?
accessing. That will be private. You can
Shared.
declare that from within
If you make it
your
private,
scope
it's
of
destroyed
your
when you finish
parallel
your
section.
computation.
So you don't even
So A
need
is
to
shared.
declare it outside. You
AS
only
is
use it
shared.
on the inside, so you can
The thread
define it
ID
whenever you
will
like.
be private. You will have
Good
a
luck.
new variable, int index, which
Before the end
controls
of
which
class,
part of the array
I
your
want you to
each
show
thread
me
is
both
accessing.
codes.
That will be private.
So before you
can
leave,
declare that from
before your
within
body takes you
your
out that
scope
door, I
of
want
your
to see the
parallel
code.
section. You don't
But
even need to
should be
declare
pretty
it
easy for you to
outside. You
do.
can use it
We
on
still
the
have
inside, so you can define it
hours. This should only take 5 or 10 minutes,
Before the end
but
of class,
take your time.
I want you to show me
Muck
both
around. I
codes.
want you to play around with this.
So before you
I want to
leave,
see if you guys
before
can
your
make my
body
computer
takes
crash
you out that door, I want to see the code.
in a healthy, normal way
But
by destroying my
should be
machine.
pretty easy for you to do.
Once you've
You
got
still
your
have
result, show me. If you can't get your code to work,
this should
come and
only
see me
take
or put your hand
5
up.
or 10
I'll get your
minutes,
code
but
working.
Take your time.
All right, good luck, people.
Muck around. I want you to play around with this. I want to see if you guys can make my computer crash in a healthy, normal way by destroying my machine. Once you've got your result, show me. If you can't get your code to work, come and see me or put your hand up. I'll get your code working. All right, good luck, people.